Everyone. In our last video, we introduced the heat equation and used a method called separation of variables to come up with the eigen functions and eigenvalues that emit non-trivial solutions to the problem. But it sort of wasn't really clear what we were supposed to do with all those things. And so now we're going to do an example of exactly how you use those eigenfunctions to find a solution to a problem. So this is example 4 in the textbook. And the problem that we're given looks like this. du dt equals 7 d squared u dx squared. And then our boundary conditions like we're used to. And our u of x0 is, instead of being f of x, we're actually going to be given some function. It's got some signs in it. 6 sine 5x. And then what I didn't fill in was where these things are good. So this is for x between 0 and pi. The length of our wire in this case is pi. Seems like sort of a weird length for a wire, but when we've got signs in our problems, we know that that's going to make our numbers work out a little bit better. Our middle condition, our boundary conditions are for all t positive, and then our initial conditions are for all x between 0 and pi. So here's our solution. So we have beta equals 0 in this case, and our L equals pi, just like we said. And we know that we can't have a trivial solution to this, because if our u was identically 0, then u of x0 would equal 0, and it wouldn't equal 3 sine 2x minus 6 sine 5x. So the only option we have for finding a solution is going to be something to do with the UNs. It's conceivable that there could be some other solutions that we haven't been able to find, because remember, we made that really strong assumption at the start that our solution is separable. But in any case, those are the only things we know what to do with. And so let's hope that we can, let's see, can we find a linear combination of the eigenfunctions. And those eigenfunctions looked like un of xt equals cn e to the negative beta n pi over L squared times t sine n pi x over L. So can we find some linear combination of these guys? Let's put this in a box. That satisfies the initial condition. So in other words, we'll use yellow since we're plugging in our initial condition. We need u x0. If we add up some cn, and now we're plugging in t equals 0, so we get e to the 0 times sine of n pi x over pi. So that's going to be our sum of cn sine of n pi. And then we need this to equal our initial condition, which is 3 sine 2x minus 6 sine 5x. Okay, well, that's pretty easy. Just take cn equal, or let's see, we'll take c2 equal to 3 and take c6 equal to negative 6. And then cn equals 0 for all other n. So what does that give us? That gives us our u of xt. Let's see, let's remember what our eigenfunctions look like. U of xt is going to equal, we'll get a term for c2. So let's see, 3 e to the negative, beta in this case is 7. So 7 times, and for this term is 4, and the pi's cancel, times 4, n is 2 times 2 squared, t, and then sine of 2x minus 6 e to the negative 7. Now in this case we have n equals 6, so we have times 6 squared t sine of 6x. So what we have, this is the u2 of xt, and this is u6 of xt. And so this is actually our answer. This is the solution that we were looking for. Now, you might think, well, that's kind of like a really easy, a really conveniently easy initial condition that we had, that we could just sort of, that it had the exact form of our un functions. So we might want to ask, you know, what about an arbitrary initial condition f of x? So it turns out that almost all the f of x that we might care about can be written as some sum of those sine functions that we had. So Cn sine of n pi x over L for x between 0 and L. So the really nice, easy, going back up here, the nice, easy initial condition that we had was obviously written as a very short series of sine functions. But now in an arbitrary case, as if we can write our f of x, which we can in a lot of cases, if we can write this f of x as this sine series, then, so if that is our initial condition, then we've got our u of xt already. We just take our c's from there and we sum up all of our eigenfunctions. So we get the sum from n equals 1 to infinity, our coefficients from the sine series, e to the negative beta n pi over L, let's see, over L squared t times sine n pi x over L. So this sine series right here is called the Fourier sine series. And it's really important in how you find those C's and how you prove that this series converges and all that is part of the some theory that we will talk about a little bit more over the next couple sections. And it's a bit like having a power series representation of a function. Instead of having power functions, instead of having powers of x, you've got these sines of x. And what makes this a lot more useful than power series is that, sort of by definition, only analytic functions admit power series representations. And analytic functions are really, really nice functions. You can take infinitely many derivatives of them. They're very smooth. But a lot of the functions that we'll see in real life aren't as nice as that. So what is useful about sine series is that they can represent more of the useful but less nice functions that we will see in applications. So that's all about that example. For section 10.2, we're going to do one more example and then that wrap up the section.